Welcome to our capstone presentation. Our capstone project is called C² Smart Glasses, and our group is comprised of Thomas Kaunzinger, Lauren Javan, Mohammed Laota, Jullian Liang, and Andrew Nedea.
The C² Smart Glasses are actually an attachable device that can be used with any pair of glasses. They were created with a goal to help those that are hard of hearing communicate more easily with others. The glasses accomplish this by transcribing a conversation and providing real-time subtitles for the user. The important components of the smart glasses are the Bluetooth connectivity, the Android mobile app, which employs Google's transcription API, and the optics.
Our system is comprised of numerous interconnected physical, electrical, optical, and software components. Starting with electronics, the C² relies on a Raspberry Pi Zero-W microcontroller. This microcontroller is powered by a rechargeable battery module, and this Pi reads in audio from an I²S MEMS microphone, to which it relays that audio to Android via Bluetooth. The Android device retrieves transcriptions and sends them back to the Pi, which then drives the OLED display with said transcriptions. The OLED light is manipulated with carefully designed optics to enable the user to view the transcriptions in a comfortable manner. And finally, all physical components are contained within a custom designed and 3D printed enclosure. I had designed the physical module to have enough space to hold the Raspberry Pi alongside its battery module. The MEMS microphone was mounted near the front, and the OLED alongside its appropriate optics were fitted to direct light into a user's eye. The acrylic partial mirror is adjustable to align with anybody's eyes, and the clip design was made in such a way that it's compatible with nearly all standard glasses frames. These models were designed in SolidWorks, sliced in Cura, and printed on my modified Wanhao i3 printer. There were many iterations before this design was perfected. Fortunately, due to the low cost of 3D printing alongside our cost-conscious components choices, we were able to keep the cost extremely low. One unit of a C² glasses attachment amortizes in cost to a little under $60 in raw materials. By far the most expensive component in the system is actually the battery. To ensure that the user is able to see the transcriptions, we had to design an optical setup that would project the OLED's light in such a way that it was clearly visible, but non-obtrusive. We had used Professor Chuck's optical expertise to pick out a lens that would increase the image size of the OLED while also projecting the image in a manner that the human eye perceived it as roughly 1 foot away, despite being much closer in reality. Extra attention was necessary to ensure that the lens and mirrors did not act as unwanted apertures and that the image appeared sufficiently far away as to not appear blurry. Prior to designing the enclosure, I had designed small optical test pieces to ensure the image would appear correct.
There are many parts to our software system, but the flow of data is fairly intuitive. This diagram shows the typical flow of data from the moment someone speaks to the rendering of transcriptions on the device. We start with the audio thread, which is constantly listening for speech. When speech is detected, it sends the relevant audio data to the Bluetooth server to forward to our mobile system. When the mobile device receives audio data, it forwards that again to Google, where a transcription is generated and passed back to the mobile device. The mobile device then forwards the transcription data back to the Bluetooth server, which notifies the OLED of a new transcription, like we discussed earlier. After that, the OLED adds this text to its stored transcriptions and scrolls the window. The Bluetooth server was designed with future extensibility in mind. We implemented this using a publisher-subscriber architecture. A subject is an enumeration of topics that could be of interest to other software components. The most useful example of a subject in our project is transcriptions. A subscriber is an interface that defines a single public method which consumes information of interest. In the case of a transcription subscriber, it consumes a string representing the new transcription. The Bluetooth server maintains a dictionary that stores a list of subscribers mapped to each subject. Subscribers are added to these lists using the register subscriber function. Whenever information related to a subject, such as a new transcription, becomes available, the Bluetooth server iterates its list of subscribers for that subject and calls their update function. We wrapped our OLED driver code in a class that implements transcription subscriber. We then registered the OLED to the transcription subject. This means that whenever the Bluetooth server receives a new transcription, the OLED is notified. The OLED handles new transcriptions by appending the new transcription to its currently stored text. It then scrolls the display downwards as needed to make room for the new text.
To establish communication between the user's mobile device and the glasses, we use a custom Bluetooth protocol based on RF-COM. This has the advantage of having minimum overhead and being reliable, similarly to TCP. The protocol enables quick two-way transmission of 16-bit audio and text transcriptions between the mobile device and the glasses. The protocol is also modularly designed such that other features, like translation, for example, could easily be implemented. For speech transcription, C² leverages Google's transcription API to convert the audio input from the glasses to transcriptions that are then rendered on the glasses display. This has the advantage of being low cost, and that Google's transcription API is free up to an hour a month of usage, and then only $1.44 for every hour of audio transcribed afterwards. The transcription is done by using a mobile device connected to the internet, acting as a relay. The mobile device simply forwards the audio to Google and reads back the transcription to the glasses. The battery drainage on the mobile phone is negligible, as well as virtually all transcription work is offloaded to Google.
Prior to wrapping up, we would like to provide for you a quick demo of our product in action. Hello, this is Thomas here, and I am going to show a very quick demo before I put it all together of the Bluetooth transcriptions in action. So to begin, we're going to run the start script, and I'm going to have to be a little bit quiet until the application starts running. Okay, so we're going to go start, and you can see here, ready to open app. So we run the app. Accepted connection. And now that we have accepted connection, I am going to be talking. Well, I mean, it's not completely accurate, but it is transcribing indeed. Here you can see the application working as intended. I am speaking to the MEMS microphone on the Raspberry Pi, and it is sending that through Bluetooth to this tablet, which is sending the transcription back to this Raspberry Pi. This is a test to show that these glasses work in untethered operation. Here you can see our transcriptions in real time. Sometimes the transcriptions are not always accurate. You can blame Google's API for that. When looking from the front, it is very hard to see anything. Here you can see some pictures of me wearing these stylish C² smart glasses. I have no doubt that these will be the hottest fashion trend of this year. Anyways, back to the rest of the presentation.
While we had a rather smooth progress through most of our development of our capstone project, we did run into issues when we had to integrate each component. First off, we had a myriad of Bluetooth issues, such as profile configurations that made us drop the idea of having an iOS app and move forward with an Android app, poor connections with the Raspberry Pis, inconsistent Bluetooth behavior, and incompatible audio format for transcriptions. we had to also come up with how we would want to attach the device to glasses in a way that was stable and universal for all frames. This led us to design a clothespin-like design, which worked fairly well. Lastly, our omnidirectional microphone picked up a lot of background noise that we had to programmatically filter out so our transcriptions can be more accurate.
The first main improvement that could be included in future iterations of this design is the ability to translate the conversation from a foreign language. This would expand our target audience drastically and make our product more marketable. Another improvement is for the hardware components to be smaller to ensure that the load of the device is evenly distributed and to make the fit more comfortable for the user. And finally, a better filtering system for the audio to ensure that only the most important audio is recorded and sent to be transcribed.
Anyways, with that, this concludes our capstone presentation for our C² smart glasses. We would like to thank all of our friends, family, and significant others who have supported us along the way. We would also like to give an extra special thanks to our professor and friend, Chuck DiMarzio, whose guidance has proved pivotal in achieving our goals. On behalf of our entire team, I wish you all a fantastic winter break and great success in your future. Thank you all again. Adios.